Hello, George Romanic here. In few of my previous videos I talked about pressure and density and how these variables change with the altitude in our atmosphere. In all of these cases, the lectures were theoretical and we derived some equations and talked about various terms and so on. Today I would like to perform a couple of experiments that will demonstrate the nature of the pressure in our atmosphere and really the force that the air around us and the atmosphere therefore exert on us and all objects close to the Earth's surface. And you will see its enormous force. I would like to bring your attention to my video on hydrostatic approximation. You will remember in that video we demonstrated that 1 atmosphere of pressure corresponds to approximately 10 meters of water, depth of water of 10 meters. And that means that using suction, you cannot bring water to higher elevation than approximately 10 meters. Since I live on the 2nd floor and I calculated that the height of my balcony is approximately 7.1 meters, that's a perfect experimental setup to get one of these tubes. In this case, this one is about 8 meters long. So one end of this tube I stick in the jar that contained cranberry juice and that is at the surface, and the other end I put in my mouth and I try to bring the liquid to 7.1 meter height, and that is not an easy task, as you will see, because 10 meter is theoretical maximum. I will also perform 2 other experiments, but they are self-explanatory, or at least I think they are, and I will try to explain them as I am performing them. I hope today's lecture and these experiments will help you to better understand atmospheric pressure and the force the atmosphere is exerting on all of us. Let's get started. We will take a can of my favorite pop. Of course, I'm not sponsored by these people, but spending more than 5 months in Italy, I developed love for this juice, and a big shout out to my Italian friends. I take a lid, so I drank this. I take a little bit of...
That's the cold water.
Oh, sorry. Yeah. This one will be a lot of fun, as you will see. I drank it, and now I put a little bit of warm water. It doesn't have to be warm, but it helps, because now I will boil water in this can. So it will take us some time. Here I already have prepared cold water. When this boils, it has to boil for some time. Then we will get back to it and I'll show you something amazing. Okay, let's try this experiment. The height is about 10 meters, 9-10 meters. I will try to bring this liquid to this height using just my lungs.
Yes.
I managed. Woo! Oh my God, I managed. I can barely breathe, but this was so difficult. So difficult. This is from another perspective. Liquid all the way in the tube, almost to our height. Come on, you can do it. There we go. Very, very nice. Very, very nice. Okay, let's discuss the physics of all this business of bringing liquid to higher elevation. What is going on is the following. As you can see, this tubing is again in the cranberry juice, and there is hydrostatic pressure from the atmosphere pushing on the surface of the liquid. Now, there is no liquid in the tube because through this tube, again, hydrostatically, atmosphere is pushing back into that liquid and everything is at the same level. However, when I put this tube in my mouth and I expand my lungs, because I expand the volume of my lungs, pressure decreases inside of my lungs. Because this end is exposed to the pressure in my lungs, and at the same time the rest of the fluid over there experiences hydrostatic pressure of the atmosphere, well, that atmospheric pressure is pushing liquid into my lungs due to the pressure gradient force. So when I do this, So when I do that, I'm constantly keeping the pressure in my lungs low. The atmosphere is at the same pressure. It is pushing the liquid. Liquid has nowhere to go but through this tube all the way to my mouth. Another very interesting thing is, you see how easy it was to bring the liquid to this height using the same length of the tube that we used at the balcony. And that is very, very important fact in these types of fluid related phenomena. Whenever you are dealing with gravity, the length of the trajectory or anything that is perpendicular to the gravitational field doesn't count, which means this tube could have been 10,000 kilometers in the horizontal plane, but only half a meter high, and I would just need to suck the liquid half a meter high. That much energy would be required, except for one small detail that is extremely important. That's if we neglect friction. However, there is friction in everything, including this tube, and therefore the longer the tube, the more difficult will be to suck the liquid, but not because of the gravitational forces, if everything is in horizontal plane, but rather because of the friction that takes away energy and reduces also the pressure gradient. So this is very interesting experiment. I highly suggest you do it at your home, and you will learn a lot about fluid dynamics. The water is boiling, and I believe it's boiling for quite some time now, or rather long enough time. It's completely warm. What I will do now, I'll take this tool, take this quickly, and put the hole into the water, and let's see what's gonna happen. Did you see that? Did you see this beautiful phenomenon? Huh? Did you also see how instantaneously it happened? Let's describe what happened in this can. The can was warm, but that's not the reason it imploded. The reason is it was full of water vapor. When I took it and I put it upside down in this cold water, the water vapor condensed, which means it reduced the pressure inside, and the atmosphere shall not have that. The atmosphere pushed inside and immediately imploded this thing. This is absolutely beautiful experiment. It's also pretty safe because the thing is imploding. It is not exploding. Another easy experiment that is very nice and can be used to demonstrate hydrostatic pressure and the mass of the air everywhere around us is the following. You take a sheet of paper, just like this one, regular paper, and a piece of wood. In this case, this wood is perhaps half a centimeter thick, not more than that. Now, 1 atmosphere of pressure is about 10,300 kilograms of force per square meter. This sheet of paper is around 56 centimeter wide, 71 centimeter long, and that means there is approximately 4,000 kilograms of force on this area, on this sheet of paper, and that is a lot of air, huge mass of air impinging through hydrostatic pressure on this piece of paper. Now we know, through Newton's law, the paper is pushing back. And now the experiment. You take a piece of wood and you put it under the paper, just like so. Now, of course, you don't have to be Einstein to recognize you can lift paper with this piece of wood. No problems. But you do this. Oh my God. I'm not supposed to block. Did you recognize what I did? Oh. Fortunately, I have another piece of wood here. Oh. Let's take another piece of wood. Now I didn't block. Did you see something remarkable, guys? This piece of paper did not go up. Why? Why is that the case? And that has to do with the first Newton's law. And the first Newton's law, law of inertia, says if you have an object that is sitting still or moving at constant uniform velocity in straight line, it wants to stay like that. Now, this paper is sitting here and there is 4 kilograms of air on top of it. When I accelerate these 4 kilograms of air like this is very small acceleration and it will take it, so to speak. But when I hit here suddenly, I want to accelerate huge amount of air suddenly, and it is pushing back. And it is pushing back with the force that is so high it can easily break a piece of wood, such as this one. At the end, I would like to make a few remarks. Remark number 1 is, I hope this video helped you to visualize how challenging it is to bring water, or for that matter any other liquid, to high altitudes. So if you, like me, live on the 2nd floor or above in a building, I hope you will realize it's not so trivial to bring water to these heights. In fact, it is impossible without a pump. So there is a pump bringing water. Every time you turn on your tap water, there is no problem, you know the water will run. But in the background there has to be some pump pumping the water to those heights. It is even more interesting to think about it in the following way. That pump requires electrical energy to run, and quite often that electrical energy comes from a hydropower plant. And hydropower plant works on the principle that there is water falling from some height on turbine blades. They run generator, the electricity goes into the system through transmission lines, comes to your pump in your home and pumps the water up. So if you think about it, perhaps if the energy comes from hydropower plant, there is water falling from some waterfall, let's say, falling down, generating electricity so that that electricity can be used to lift water to high elevation in your apartment, for example. So water falling down is used to bring water up. Very, very interesting. Remark number 2 is I hope this experiment showed you the beauty of atmospheric sciences, fluid dynamics, how interesting it is to study these things. You get to understand how world around you works and so on. And remark number 3, which is very important in my opinion, is quite often you go to a, let's say, cafe bar with your friends and family, and then you start talking to them about your life or something related to your life, and they tend to do this. After a few minutes of you talking, they start doing this. And they start playing with water like this. Now I'm sure most of you thought that these people are just bored and they don't want to hear what you have to say. But after this video you can reconsider that. Perhaps they're just testing hydrostatic approximation, atmospheric pressure, thinking about these things. So think about it. Also, if you are the person that perhaps is bored when someone else is talking, you start doing this, and they ask you, are you bored? Am I boring? You might say, no, please tell me more. I just test hydrostatic approximation in our atmosphere. Until next video, goodbye.